Where'd we leave off? Silicon?
Yes.
Okay. Did I show you the allotropes of carbon?
Yes.
Let's see them again. I feel like I went through them very quickly.
Are you sure?
Yeah, you were. That's what you were.
Yeah, so we're gonna do that again.
That's
All right, so here we go. Allotropes of carbon, and they are what again?
Graphite.
Graphite, diamond, and
Buckyball.
buckyball, right? And the diamond. So here's a single diamond. Okay, so there's diamond. Ben, you want to help me out here? Just get this one. There's the simplest unit of a diamond molecule, we'll call it. So you have multiple carbon atoms bonded to each other. That's a covalent bond between those two. Fairly strong. Diamond's very, very strong. It gets stronger the more of those units repeat. So as it starts to build and it gets bigger and bigger and bigger, then it kind of looks like that. Okay, so that's diamond. It's three-dimensional, very rigid, repeating pattern. It forms a crystal structure, and it's very hard because the bonds are strong. Strong bonds, in this other phrase, strong intermolecular forces. You're going to hear me say that all year. If there are strong forces or strong bonds like diamond, it's very hard to melt because the particles are so rigid, so tightly packed and attracted. When you melt them, they have to separate a little bit and start to move. So if they're held with really strong bonds and forces are actually more important than bonds. I think I used some analogies there. So gravity is like a force. Okay, if I jump up and come back down, you can't really feel it, not really. You can't touch it, you can't see it, but it's there. So forces of attraction in chemistry between atoms and molecules, kind of the same thing. It's like this force it's there, but you can't really see it or feel it or touch it. So anyways, the stronger it is, the stronger those forces, the harder it is to melt or boil or evaporate, any of those things. So diamond's really strong. Graphite is also strong. It exists in sheets. So like this could be a thin sheet of graphite. If you were to take a piece of paper, shade a little spot with pencil, and take some tape, put it on top of that shaded area, peel the tape off, then fold the tape in half, and then peel the tape apart. On the part that you peeled off, one of those sides, you should have what's called graphene, which is one atom thick layer of graphite, which is what this is. So it's very, very thin, obviously, and it's very flat, thin, flat, whatever makes sense to you, kind of like a sheet, like sheets of paper on top of each other. So this is like one sheet that I would be looking at from this perspective, looking down with these little hexagons. These are double bonds, stronger than single. The individual sheets of graphite are actually really strong. Pretty comparable to diamond, but where graphite gets weak is in between the sheets. And that's why I use this part of the video. Back up. There. So in between, there looks like nothing, but actually between these sheets, there are these forces of attraction I'm talking, like gravity. There's something attracting these together so they stay sort of close to each other. So graphite is a solid, okay? So they're pretty close. But in between these sheets, those forces are actually pretty weak. So weak, you can just rip the sheets apart by just simply touching a pencil. It'll come off on your hand. That's because the sheets are sliding off of each other onto your hand or onto paper. So graphite, in general, is a lot weaker than diamond, and that's just because of those weak forces between the sheets. If they had strong forces, they would actually be right on top of each other, and they might even bond. Bonds are stronger than forces. All right? So I'm saying a lot of things. Diamond is more rigid. Diamond has stronger forces, stronger bonds. Graphite has weaker forces. You don't need to know all of this, like memorize everything I'm saying. Just in general, diamond's stronger than graphite. And buckyball, called a fullerene. Here's carbon 60, that's buckyball. And I think they're going to do a carbon 90 is next, perhaps. Carbon 180. I don't know if there was a 90, but anyways, it's just a little bit bigger, right? But you can see the shapes there. What's that one? Trigon. Trigon, I just said try again. Hexagon, pentagon, right. So that's in this hollow. And that's a buckyball molecule. And again, they're found in like soot type material. Weaker than diamond, comparable to the strength of graphite. Again, you don't really need to memorize that, but that's the allotropes, right? So depending on how the atoms are arranged, it changes the properties. What they look like, how we use them in society, what we use them for, their value, right? So just because the carbon atoms are arranged a certain way for diamond, we value that over how graphite is arranged. Sort of. Why are diamonds expensive? Why do we value them?
They're shiny.
A lot of things are shiny.
They're pretty.
Aluminum foil is shiny.
They're worth a lot of money.
Why are they worth a lot of money?
The way they're made.
Why is anything in this world usually, things that are really expensive, why are they usually, right, so it's rare, right? Diamonds sort of are rare. Does anyone know where I'm going with this? I don't know a number, but I do know if all of the diamonds in the world that have been mined, that are available, are released into the market for people to buy, they would be worth pennies. So they're not rare. So why are they expensive? Because these companies that mine diamonds and then the jewelry companies that sell them, they just decide to only release a little bit once in a while to make sure they make a lot of money off it.
That's smart.
Smart, also kind of an evil thing to do, personally. And a lot of diamonds are sourced from really, really poor management. Well, what's the word I would use? People die. Kids die. There's a lot. You ever hear of a conflict diamond? From like Africa? Yeah. It's, if you ever want to look into it, Google that. So a lot of diamonds come from places where kids are forced to work and it's really bad. They die trying to find these. Anyways, blood diamonds. Anyone hear that phrase? So a lot of times, like, let's say someone's gonna, wants to get married, get engaged. Any of you want to do that in the future? My opinion, try and find out where the diamonds are from and if it's, from an area where that's happening or not. So they're called blood diamonds. Anyways, I could go on and on about that. That's not chemistry related, but just life related. Moving on. All right, so silicon. We did write it down. Someone told me, yes? No? All right. Bell rang. Lights, please, Tristan. All right, so we left off on carbon then. Now we're on silicon. 28 I have till, right? Yes?
Yeah.
All right, here we go. You don't have any homework, by the way. Okay, here we go. Silicon. All right. SiO2. That's what we call quartz or sand. That is something you should know in this class. The compound for sand or quartz. Silicon dioxide, SiO2. Very hard. Very strong. Like diamond, actually. Except not as rare. There's lots of sand on the earth. What else do we use silicon for? I've gone over it many times. Photovoltaic cells. You with me, Cody?
Yep.
Okay. Photovoltaic cells. And where do we use those? Solar panels. Right. Also computer chips. And FYI, not really a Regents thing, but you learn this in earth science, silicon is the most I said the most. I'm looking at my notes and I'm like, I think that's wrong. It's the second most abundant on the earth. Second most abundant element. It's found in the ground all over the place. What's the first? The most abundant?
Rock.
That was priceless, Cody. Let me rephrase that question. So silicon is an element, and it's the second most abundant element. What's the first or the most abundant element?
Oxygen.
Very good. Oxygen. Oxygen, the most abundant. Why? It's in the air and
Water.
and
Water.
Dirt.
dirt.
Ground.
What'd you say before?
Rock.
Rocks, right. So silicon SiO2. You ever hear of silicates? Like in earth science, silicates? I mean, I know I taught earth science lab many times. I know in the reference tables we talk about this, but anyways, yeah, oxygen's in a lot of the ground, right? Land, water, obviously, H2O, and the air. So anyways, most abundant. We breathe that. That's what we breathe. What's ozone? It's not O2, it's O3. That's ozone. What does ozone do? Protects the earth from harmful cosmic rays, ultraviolet radiation, all types of other stuff, okay? Yeah, without the ozone, we'd be in trouble, okay? So the ozone is kind of a protective layer. So that's O3. Again, that's something maybe you don't need to memorize in here, but it's good to know. We talked about nitrogen before. We talked about sulfur, zirconium. Where's zirconium used? ZR, where's zirconium used? This one right over here. I think we talked about it in here, maybe not. Well, you don't have to buy real diamonds. You can buy cubic zirconia, right? Fake diamonds, right? Save a lot of money and they look the same. So who would know the difference, right, Cody? You pull a fast one. Good luck. When they get it appraised, you're in trouble. All right. Tungsten is in filaments. W. Old light bulbs, incandescent, right? We should be using CFLs. Actually, LEDs is what we should be using now. I know I'm kind of doing this out loud. We talked about that. Raquel's allergic to it, and you need to know what it does. Iodine. Sorry, I didn't mean to call you out, but we should all know that because we do deal with iodine sometimes. But obviously, we'll keep it in the fume hood away from you. Yeah, iodine. What does it do? I think someone just said it.
It cleans.
Someone else.
Don't
It
they
goes
just
from a
like
solid
MRI?
straight to a gas. Sublimes, right, sublimation. So I2. That's supposed to be a 2. Iodine, sublimes. What does that mean? Goes from solid to gas. Is helium flammable?
Yeah, no. But-
Helium's over here. Group
Yeah.
18, is it flammable?
Yeah.
No.
No.
If something's flammable, guess what it's doing? Reacting. Group 18 doesn't react. Is hydrogen flammable?
Yeah.
Big time. Okay? Just keep that in mind. Those over there aren't hydrogen very flammable. You ever hear of the Zeppelin? Burned up? Talk about it some other time. So I gotta do one more thing before the bell. 7 diatomic elements. 7 diatomic elements. These elements exist in pairs. They do not exist as atoms. So for example, iron can exist as atoms of iron, one individual atom. This is an atom, so there's an atom. These exist like that. That's 2 atoms called a molecule. So these 7 elements, H, O, N, Cl, Br, I, and F, those 7 exist in pairs. We call that diatomic, 2 atoms. So underneath each one here, we put a 2 in the bottom right corner. H2, O2, N2, Cl2, Br2, I2, and F2. They are called the 7 diatomic elements. They are unstable as atoms, so they pair up with themselves. And that makes them more stable, the whole valence electron thing. I prefer to call them Hunkelbrief. That's the phrase, Hunkelbrief. So I'll say, what are the Hunkelbriefs? And you would say the diatomic elements. So all of them exist in pairs, and that is just something that you need to memorize. Okay? Not necessarily why. I told you why, because they're more stable, but remember those. All right? And that's it, obviously. Bell rang. No homework. I'll see you tomorrow.